So what I'm going to discuss here and to present here is I'm going to give say a general overview of a method that we have been working on together with Diogo, and also with works involving Tigran Bakarian and Teru Tada, where we use monotone methods, ideas to address mean field games. So I'm going to give a sort of a general overview on those works. Let me start. So the first slides probably are familiar for all of you, or at least most of you, but just in case, I wanted to make sure that I would be on the same page with everyone. So allow me with some first slides with very general facts. So first of all, about the mean field game theory, which addresses the study of strategic decision making for large populations of agents that are rational and identical, and they compete and seek to optimize a certain utility function. And one feature of these mean field games is that each agent only considers statistical information of the population rather than individual information on each agent. And these mean field games were introduced more or less 15 years ago, more or less also simultaneously in the engineering community by Keynes and his co-workers, and also in the mathematical community by Lasry and Lions. And these mean field games, actually, they appear in several applications, and these include, for example, crowd and population models, chemotaxis, herding and flocking models, economic growth and socioeconomic problems, price formation and price impact, traffic flow, and many more. And the general framework of mean field games is as follows. So we have an unknown, a probability density M that represents the population distribution. We have another unknown, the potential pressure or value function U, that encodes the effects of the population in the environment. And these two unknowns are solutions of a problem, and typically U is the solution, or solves a nonlinear elliptic or parabolic equation that depends on M, and M solves an evolution PDE that is driven by the potential U. And this mathematically can be written as a system of two equations, and a Hamilton-Jacobi equation that is usually considered as an equation for U, and a Fokker-Planck equation or transport equation, which is usually seen as an equation for M. Of course, this is a coupled system, so this is what I'm saying does not really make sense, because both equations depend on both unknowns. But this is in general how people see the mean field games, how the interpretation of the mean field games. And to give an example, for us to see some examples of mean field games and things that I have in the back of my mind. So here is a simple example, this first one, a simple example of a mean field game, which is a time-dependent mean field game. So here, H is the Hamiltonian of our system, is a data, so it's known, and it is related to the cost function and models the interactions between agents. We are given the initial distribution of the population, so this is a known, and we have terminal cost. So U satisfies a terminal condition, M satisfies the initial condition. And here, in this example, sigma could be either 0, in which case we are in the first order problem, and this models deterministic dynamics, or could be different from 0, in which case we are in the second order and models stochastic dynamics. And here, what I have below is the corresponding stationary case that captures the ergodic equilibrium and corresponds to the long time behavior of the time-dependent mean field game. Again, just a few more general things about these mean field games problems. Hamilton-Jacobi equations and Fokker-Planck equations per se, they are very well known, very well studied. So people know most things about these two equations. The thing here with mean field games is the coupling. The coupling between these two equations, it raises non-trivial existence, regularity, and uniqueness questions. And of course, because mean field games also they model different problems with quite different features, and so as we can imagine, they cannot be addressed by a unique common method that encompasses all cases. And also that's something that is also known. There are cases that it has been proven that mean field games actually fail to have classical solutions. So there is a need for an appropriate notion of weak solutions. And this is actually going to be the main topic of what I'm going to present here today. And also in several of the cases that I'm going to present here today, they concern the first order case. So in the previous slide, when sigma is equal to 0, and the difficulty there, as opposed to the second order one, is that the Hamilton-Jacobi equation provides little a priori regularity. So the first order case presents can seem in some sense a little bit more challenging. And on the literature, so this is for me one of the most difficult slides to have. Even the mean field games are relatively recent, but the literature is already quite vast. There are several quite important results in the literature, but this would always be a very bad slide, because either it's very incomplete, I just present some and then I'm missing many others, or if I present a list of names, there is always someone missing. So I prefer to refer to there are books in the literature, there are several review papers, and I hope when we wrote our papers we did a good job in citing to whoever has credits for. So, but here allow me to skip names and particular references, and what distinguishes, not necessarily better or worse, what distinguishes the approach that I'm going to discuss here from many of the works that exist in the literature is that many of the approaches, they are in some sense problem tailored. So we have, say, this mean field game, and then we are going to study it with the people developed methods, arguments to study and derive very important and strong results for that mean field game. But then these techniques, because they are very attached to the kind of problem they have at ends, they don't translate necessarily to other problems. And what we were trying to understand was, say, a common denominator, not to all mean field games, but at least to a very broad class of mean field games that could somehow be tackled in a similar way. So this was our idea was more of a broad scope approach rather than a very specific and tailored one. And this is based on monotonicity methods. Now, why monotonicity? Because actually many mean field games, they share this common feature. They encode some kind of monotonicity, and these include local and non-local mean field games with or without congestion, first or second order cases. So, and also including non-degenerate mean field games. So this is really a feature that is out there for many mean field games. And what monotonicity encodes is crowd aversion. And because there is crowd aversions, agents tend to spread evenly. And from the mathematical point of view, uniqueness, existence, and regularity are derived based on these monotonicity properties. So having said that, let me first now make a detour into these monotone operators and the variational inequalities, because the path that we follow for the mean field games really mimics this very well established theory on monotone operators. So this is going to be a detour and a crash course, but I forgot the slide that I had before, just to show you an example, a simple example, and to show you what is this monotonicity that I'm talking about. So, for example, let's consider this stationary mean field game problem, and what we want is to find U and M with M non-negative. It is the density of the distribution of the population that satisfies this problem. And here I'm working on the torus. So that means that I'm working with periodic conditions in space. And this is the stationary case, so no dependence on time. And like I said before, usually people see the Hamilton-Jacobi equation as an equation for U, though it depends on M, and the Fokker-Planck equation as an equation for M. But if we reverse the roles, meaning, so I can rewrite this system of two equations as this operator M, in which I'm putting M, say, in the first row, which in principle would be an equation for U, and U on the second row, which in principle would be an equation for M. So I'm reversing these roles. So I can rewrite this system as this one. So where here it is just a definition of the operator, and this is just corresponds just to the left-hand side of my equations in the system. So this is just another way to rewrite the problem. And then what? Well, if I compute this inner product, so if I take two pairs, M1, U1, M2, U2, I make the difference of the operators evaluated at these two pairs, inner product with the difference of two pairs in the product space in O2. Elementary algebra, just integration by parts, mainly integration by parts and associating the right terms, we get this integral term. And this is monotone because M to the alpha is a monotone function. So this is no negative. And this part, because I'm taking M's to be no negative, this is my domain. This is also a no negative term. So the sum of two no negative terms gives a no-negative quantity, and what this is saying is that A is monotone in L2, cross L2. And this is not a new observation. This is not something that we take credit for, because this computation is at the heart of the proof of uniqueness by Lasry and Lions, uniqueness of smooth solutions by Lasry and Lions. But as you see, so the point here, and that's why now next I will talk about monotone operators. The point is, I have this mean field game. I can rewrite as an equality with some operator, and this operator is monotone. Okay, so I stop here in terms of mean field games. Now I make a detour on the theory on monotone operators, which then I'm going to import to address mean field games. So if H is a Hilbert space, A monotone with a certain domain, then this is just a definition. A is monotone if this inequality holds. And of course, the most simple example of a monotone operator that we can come with, I guess, it's a real valued function, increasing real valued function. So this is the simplest case of a monotone operator. Okay, let me go on. And then people in this business of operators and monotone operators, they introduced what they call the strong variational inequality. And this is the problem of finding a certain W star in the domain of A that satisfies this inequality. So inner product of A evaluated at W star, inner product with Z minus W star, where Z is an arbitrary element in the domain, this has to be non-negative. Now, what does it mean solving this strong variation inequality? Actually, this is nothing but solving this identity. So we are looking for the kernel of A. So and one way, so this is in the case of the domain of A is the whole Hilbert space. Of course, this can be generalized. But of course, I mean, this implication is obvious if, this implication is obvious because if A is 0, of course, this quantity is non-negative. For the reverse, if you take these pairs, you get here in the product with W no negative and greater or equal than 0 and less or equal than 0, then you get the equality for all Z in H, which of course then gives this identity. Okay, so writing this strong variation inequality is nothing but writing this identity. So looking for addressing the study of the kernel of the operator A. Now, as it happens with the monotone operators and with PDEs in general, it may be hard to prove that strong solutions, so solutions to the strong variation inequality exist, or they even may fail to exist. Now, of course, the way we in general address this kind of problem is then trying to prove some kind of weak solutions, and the question is always in which sense should these weak solutions be. And so this led to an alternative variation inequality, which is called the weak variation inequality. And this is the problem of finding a certain W star as before. But now what is the difference? So before, A was evaluated at this W star. Now A is evaluated at an arbitrary point in Z, and this weak variation inequality has to be satisfied. Now, relationship between the two of them, because of course, I mean, we want to be able to, in some sense, at least in some cases, to be able to go back and forth. Now, one thing that can be easily seen is that if it is a strong solution, then it's also a weak solution. So satisfying the strong variation inequality, then it also satisfies the weak variation inequality. And of course, then if you have more conditions, more assumptions on your operator A, then you can say out of weak solutions, you can say stronger things for them. So in particular, for example, if you start with a weak solution, and for example, if your operator A is continuous and the domain is convex, this is one possibility. Then you can prove that it is actually a strong solution. So you can, there are situations in which, depending on your operator A, that from out of a weak solution, you get a strong solution. So this is the idea. But let me stress again, because this is what we are going to see when we translate these ideas into the mean field games. So the main difference is here, A is evaluated at an arbitrary point in the domain of A, not at the point that we are looking for, the solution that we are looking for. And just for us to go back, that's why I was giving this the most simple example that we can come up with for a monotone operator. If we go back to our increasing function f, what does it mean being a weak solution? So a solution to the weak formulation, which is rewritten here in terms of the function f. Well, it means that if you take z to the left of your W star, then f is non-positive, otherwise it is non-negative. So if we know nothing, if we don't know anything more in particular that say this W star is in the domain on f, all we can say it is a point at which the f has a different behavior to the left or to the right, if we don't know more. But if, for example, f is continuous and W star belongs to the interior of the domain of f, then you get a 0. You retrieve a solution, a strong solution to your function f. But at least what in this case, what the weak solution would be, it would be a point at which f behaves differently to the left and to the right. Okay. Okay. So then, okay. So we have the, yes.
I have a question. What was the reason for going from strong to weak? It was the fact that W star, the strong solution might not exist, right?
Yes, they may not exist, or they may be hard to prove. And when things are hard to prove, what you do first is trying to have like this weak solution, and then try to establish further properties on this weak solution that perhaps gives you also stronger, sorry, yes, that's it, sorry. So let me say it again. So it may be hard to prove, they may not exist. So you start with these weak solutions. In some cases, you start with weak solutions and then you prove extra regularity and then you actually end up with a strong solution. Oh no, depends on your problem. Okay.
Thanks.
Thank you. Okay, so we started with this notion of strong solutions, maybe hard to address. We went to this notion of weak solutions, but then we still have a problem to solve. Otherwise, we would go home and done. Then how do we find the solutions to the weak variation inequality, or in other words, weak solutions? And the methodology that we are going to follow is this very well known Minton's method, in which the idea is you have to cook up a monotone approximation of your original operator. And the idea, and we are going to do this by consider higher order regularization terms that preserve monotonicity, because we want to preserve monotonicity. At the heart of all this business is monotonicity of the operator. But hopefully with these perturbations of the original operator, we hope to be able to prove strong solutions, okay? And then if they are strong solutions, they solve not only the strong variation inequality, but also the weak variation inequality. That is always an implication that always holds. Strong implies weak. So this is the weak. And then say that, and this is the idea, this is the difficulty, we have to cook up these approximations that satisfy several things for which we can find a solution, and we have to have some kind of compactness. Say that we are able to prove some compactness in H, that say my sequence of solutions converge weakly in H, and say that we have a kind of pointwise convergence. So for a z-fix in the domain of the operator, we have a pointwise convergence. Then we can just pass this inequality to the limit as strong weak. And then what we retrieve at the end is a weak solution. So a solution to the weak variational inequality with respect to the original operator. Okay, so this is the idea, and of course, then what we want is to establish further properties of this weak solution. So, but this is the idea behind this monotonicity approach that we have been developing for the last 5 years or so. And it actually started with this paper, which is actually devoted to two numerical approaches to mean field games. One of them is based on these monotonicity ideas that we then developed in this paper quite extensively stationary mean field games. And what this provides, it is a new notion of weak solutions within the mean field game literature, of course, importing these ideas from monotone operators. And we tried to prove, and we proved existence under minimal assumptions, meaning that we were trying to consider the mean field game, the agents, all the assumptions on the couplings, on the Hamiltonian, as general as possible. So we're trying to understand what were the structural assumptions that we would need in order for this methodology to go through. And actually it encompasses a wide range of mean field games, first order, second order, degenerate elliptic, congestion stationary problems. So it's really a broad scope. It was really broad scope analysis. And what this provides is a unified approach to construct solutions for a broad class of mean field games. Of course, there is a price to pay, because this is a sort of weak notion of weak solutions that, of course, then, and it's something that we also have done with Diogo in this work, then for more specific problems, for example, for the quadratic case, etc., then we extracted further properties on the weak solutions, that are not so weak as what the weak variation inequality requires. So we established further properties depending on the case when we specify further the mean field game at hand. And then, but this is stationary mean field games on the torus. So which means that we work with periodic conditions. And then we asked the question, and this was a work also with Diogo and Terutada. Then we asked the question, what about Dirichlet boundary conditions? Can we address that case or not? And as it turned out, we can. And one thing to stress is that first order mean field games and also often second order mean field games, people only consider periodic boundary conditions. But in some cases, Dirichlet boundary conditions are actually natural. And in applications, for example, when in models where agents can leave the domain and are charged an exit fee. So here, Dirichlet boundary conditions, they do make sense. And in this paper with Diogo and Terutada, we introduced a similar notion of weak solutions as in the reference I was mentioning before, but that addresses these Dirichlet boundary conditions, and also to prove existence for existence of those solutions, we adopted a different methodology. Let me give you, so that we see a bit of math, let me give you a trailer, like a trailer of a movie, a trailer version of this work with Dirichlet boundary conditions, and then I'll present a more detailed version for the time-dependent case. So here it is just a very, very, very brief overview of these Dirichlet boundary conditions. And the reason why I would like to say this is that people that are used to work with Hamiltonian Jacobi equations may object a bit with this, saying, but why should I expect Dirichlet boundary conditions to be satisfied? Because in many instances, there are no classical solutions to Hamilton-Jacobi equations satisfying Dirichlet boundary conditions. This is a very toy example here, but there are no classical solutions to these equations satisfying these boundary conditions. You don't have it. But if we add a coupling, so as in the mean field games, and then here is the corresponding Fokker-Planck equation with this coupling. If we add a coupling, in which case we are in the mean field game with the mean field game at hand, then actually we have a smooth solution, a classical solution that does satisfy the boundary conditions. So this coupling, though in general raises non-trivial questions, it also may have different, the solutions may present different features. So in particular, cases so in this case, we cannot expect existence of smooth solutions satisfying boundary conditions, but for the mean field games, there are instances in which we can, or related instances in which we can. And so in that work that I was mentioning with Teru and Diogo, this is the general the mathematical formulation of the mean field games that we are looking at here. So omega is an open bounded and domain with smooth boundary. H is the Hamiltonian, which models the cost function. G is the coupling that encodes the interactions between agents and the mean field, which is here, and V is the potential that encodes spatial preferences of agents. Agents say rather prefer at the beach than being here at listening to my seminar. And there is a function H, which is the charge, it is the exit fee. And phi is a source term that encodes the incoming flow of agents, that it is here in our transport equation. So this is our mean field game. I will no, here I'm not going into the assumptions, but they are quite mild. Let me just point out what is the underlying control problem. So the Lagrangian, which is the Lagrange transform of the Hamiltonian models, the cost function of an agent, the cost of an agent when moving at a speed v, and agents can leave the domain through the boundary at a certain time t, or they can leave the domain to a graveyard state at an exponential rate, which is encoded in the terms minus u and m appearing here in our system. And given the density of agents, a typical agent seeks to find a trajectory that minimizes this action functional. So this is the underlying control problem. And so having this problem at ends, we introduced the notion of weak solutions to our mean field game. And this is going to be a pair M. We want it to be a probability density function. U is in some Sobolev space. It's going to be a weak solution. Well, if the boundary condition, it satisfies the boundary condition, U satisfies the boundary condition at omega, the Dirichlet boundary condition. M is non-negative, it's the density distribution of the agents, and this inequality holds. And this is, so the F that is here, it's nothing but the operator associated to my mean field game exactly in the same way I was just showing in the more simple example at the beginning of this talk. So this is just the same way, and here I'm explicitly saying how it acts on pairs, because we have to make sure that from that this is well defined, but it is exactly the same idea. And again, this can be seen, say, in a certain distribution sense, but the interpretation is exactly as before. So my operator is being evaluated not at the point that I'm looking for a mu, but the operator is evaluated at an arbitrary test point. So this is the weak variational inequality. Okay, and here it is just the spaces where they live, and I think I don't say what k is, but k, it is just big enough in order to, in our arguments, is a technical value. It doesn't matter. I mean, it does matter. It is just where we can, so that we can apply some embedding theorems. It is related to that, but I'm not going to the details. It's hard to see what it is, but it is just a technical value that it is related with embedding and regularity results. And sorry, under assumptions XXX, because I don't want to go into details. I will detail everything for the time-dependent case. Here, I just wanted to give an overview, but for example, we assume that the H is convex. We assume that the coupling G is an positive increasing function, but it's really minimal requirements on our data. Under certain assumptions on those, we can prove existence of weak solutions. And in the sense that I was mentioning before, that inherits it mimics those of the monotone operators theory. And I'm not giving you the assumptions, but I'm giving you, for example, some examples of Hamiltonians and coupling functions that do satisfy the assumptions, the general assumptions that we consider in our work. And like I said, this was just a trailer version of this work, just to give you what are the ideas, and then in the time-dependent case, this I hope will become a little bit more, some of them more clear. So we start by introducing we start by introducing epsilon-dependent higher order regularization. So we start from a mean field game, we add penalization, which is a higher order regularization, okay, to the problem. Okay, just to explain why no penalization, as I said before, the arguments we used in this paper for the Dirichlet boundary conditions are different. The methodology is quite different from the one for the stationary case with periodic boundary conditions with Diogo, in which we used a certain penalization. Here, no penalization, and this is important for the numerical point of view. And then the idea is, so we have this regularized problem, and we find a candidate for M epsilon, the solution to the regularized problem, via a minimization problem. We solve a minimization problem, okay, and we find a candidate, sorry, I'm always losing my pointer. We find a candidate for M. Then we solve a variational problem associated with the convenient bilinear form. We find a candidate U. And then we prove, using these variational and bilinear problems, we prove existence of a fixed point using Schaffer's fixed point theorem. And then, of course, we have to establish some compactness properties. This is then following the Mintis method. We establish some compactness properties for this pair, pass to the limit, and retrieve a weak solution for the original problem. So this is an overview of the methodology. Now, as I said, we also applied then the two first results I was mentioning before were for stationary mean field games, but of course, at the end of the day, you also want to address the time-dependent mean field games. This is what we have done also in collaboration with Diogo Gomes and Terutada. And an important feature of the class of problems that we considered, it includes mean field games with degenerate terms, local and non-local terms for the coupling. And actually there were not that many results in the literature in these settings. Very well. So again, this is the general form of the mean field game. It's similar to what was before, but now here, I mean, the second order terms are written in this way, and this could be, as I mentioned before, and it's going to appear in the further slide, degenerate. We have our Hamiltonian. Sorry, we have our Hamiltonian and we have our coupling, and I will detail a little bit more about this. But the coupling can depend locally on M or non-locally. So we address everything at once with this monotonicity approach. We address all these cases at once. And here it is the Fokker-Planck equation. And again, as usual, in the time dependent, we have the initial distribution and the terminal cost. Omega t is our time-space domain. A are the diffusion coefficients. V is the potential. As before, it encodes time and spatial preferences of agents. H is the Hamiltonian, G is the coupling, I said this before, and also M0 and UT, I also said it's the initial distribution and terminal cost. So this is the time-dependent mean field game. So here I'm repeating the interpretation of these mean field games. Agents optimize a certain control problem with the terminal cost UT. This is the meaning of UT. As I said before, Hamilton-Jacobi equation determines the value function U for a typical agent, and while the Fokker-Planck equation gives the evolution of the agents with the initial distribution M0. And like I said before, an important feature of the class of problems that we consider, it also includes the degenerate case, and G can have simultaneously local and non-local dependence. Assumptions, so A is symmetric positive semi-definite. We assume that this mapping from M to G is monotone, so there is always this monotonicity underlying, and H the monotone is convex in P, that also in particular gives monotonicity. And under these assumptions, then we can associate to our mean field game a monotone operator. And the expressions, of course, I mean, change according to the problem that we are considering. I will not go much into the definition, but just to say that this is exactly as before. It is writing the left-hand side in the form of operator, and then doing the similar thing as if we're doing an inner product in L2 cross L2. But of course, I cannot call it L2 cross L2 because I don't have the regularity, but I can write it in L1 cross L infinity sense, duality sense, and this is what we have. So this would be the definition of F, and under in this setting, this inequality is satisfied, which is telling us that F is a monotone operator in this sense. Okay, so if it is a monotone operator, we can put all the machinery that I was describing before into play, and then we can define a notion of weak solution. And I hope by now there is no secret in this definition. It is just my operator evaluated at the test functions. Here I'm just writing the necessary functional, I mean the functional spaces that in which we can write everything and make sense of every single expression that is going to appear. Here I'm quantifying the K that depends on the dimension. And this again, as I said before, this is to be able to use some embedding theorems, but this is the definition that, like I said, I hope by now there is no much secret to it. And then again, under certain structural assumptions that this time I'm going to tell what are, I'm not going to hide anything, but this will appear in the next few slides. Under certain structural assumptions on H and G mainly, we can prove that there exists a weak solution in the previous sense to, sorry, it's not this that I wanted, but okay. There exists a weak solution to our mean field game. Okay, so this is the main theorem. Assumptions, like I said, this I said before already. The coefficients, the diffusion coefficients, the matrix of the coefficient diffusion coefficients is symmetric, positive, semi-definite. We assume that our potential that encodes the spatial and time and spatial preferences of the agents is bounded and continuous in our time-dependent domain. This K appears again for the initial data for the terminal cost and the initial distribution, and in particular the initial distribution was assume that it is strictly positive and it's a probability density. Okay, on the Hamiltonian, we assume that it is of class C2. Again, I said this before, it's convex in P, where the U appears, and we have this bound from below, these two bounds from below, and also this bound from above. These are typical growth assumptions on the Hamiltonian, on top of being convex in the variable P. And for example, because it's always good to have a non-empty set of functions that satisfy our assumptions, a possible example for a function satisfying these assumptions that I was mentioning before, it is this one. So this satisfies these assumptions. So this is on the Hamiltonian. Now, for the coupling has a non-local dependence and local dependence. For the non-local dependence, we consider an operator that is possibly a non-linear operator that goes from the space of finite positive measures on omega, absolutely continuous with respect to the Lameg measure into the space of measurable functions. So this is a mapping, and a mapping that satisfies certain conditions that we need it to satisfy. So it maps H2K functions with K as before into H2K functions. Okay, so if I start regular enough, it gives me back the same, at least the same regularity. And we also assume that this mapping is Fresh differentiable. And again, it's better that we are not working with an empty set of functions. And an example of a function satisfying these assumptions, it's written here. So it's written with convolutions. So this is a possible non-local dependence on M. And then for the coupling, we are assuming that this is a monotonicity assumption. But as I said before, this is all about monotone mean field games. So this is expected, unexpected assumption. This one, it is a technical one. Like I said, we were trying, rather than thinking of particular examples, we were trying to understand what were the structural assumptions on our data that would enable arguments. And these are quite common ones in the literature, and it has to do with establishing some a priori estimates. When you go and see in several examples what people are using to establish a priori estimates, essentially this is behind it. Okay, at least it was behind in our argument. So here we are putting in a very abstract way that G and M are controlled by, with respect to a certain parameter, by M times G plus a constant that depends on delta, of course, that it goes to plus infinity as delta goes to 0. And we have some bound from below, and this is again related with some to establish a priori estimates. Okay, so given this technical slide, one more example, one more assumption that we need, and this is to have compactness. At the end of the day, we need, if we go to apply the Mintid's method, we need some compactness properties, and actually what we prove bounds with respect to epsilon is of terms of this form, and we want this to enable some compactness with respect to epsilon. So this is plays a role in that. And again, forget about all what I said before. Take G, for example, a simple G as this. So M to tau. So this is the local dependence with tau non-negative. Sorry, with tau strictly positive. I'm sorry. This is the local dependence, and here put the non-local dependence, the example with convolutions that I was showing before. You have an explicit example that satisfy all these structural assumptions that I was showing before. And the proof strategy, it goes in the same spirit as in the Dirichlet case, which I'm going to detail a little bit more here. So we first regularize our original mean field game by adding a higher order elliptic terms. So this is what we start doing. And then we want to prove existence of solutions to that regularized problem. And that we do here again using the fixed point theorem. And then finally, step is to pass to the limit, being able to pass to the limit as epsilon go to 0 to retrieve a solution to the original problem. So this is always the same strategy. Of course, then the devil lies in the details. How can we make this work? And so here is the regularization. I mean, I know that this slide looks awful. Bear with me. So what you see here is the original terms. And then what is here in blue, it is just higher order regularization, both in time and space. This is just the regularization in the Hamilton-Jacobi equation, and it is with respect to M. And here, for the Fokker-Planck equation, a similar term, but with respect to U, higher order regularization term. And this regularized problem is complemented with a certain boundary conditions, okay? I think I say more about this, but I will not go too much into detail. This is, okay, no, I don't. I will not detail, but I will comment why do these extra boundary conditions appear? Well, first of all, one important thing is that we cannot just put any regularization to the problem. We want one that preserves monotonicity. And these boundary conditions play the role to preserve monotonicity. And also, actually, they turn out to be natural ones when we consider the variational approach. So when you look at the variational approach, these somehow are the so-called natural boundary conditions that appear. Another comment. This regularized mean field game may not have solutions, classical solutions with M non-negative, which we want, because the regularization terms are of order greater than 2, and so in particular we cannot apply things as the maximum principle. And here we are going to introduce a notion of weak solution that is not really strong solutions, as I was mentioning before for the meeting problem. Is similar, it's almost, but not really. So it requires a certain positivity, and we have to relax a little bit the Hamilton-Jacobi equation. So let me precise this. So this is the definition that we consider for weak solutions to the regularized problem. So we are now looking at the regularized problem, and it's a pair that is in our spaces that I think I didn't stop there that much, but it is just with this regularity H to K, M has to be non-negative, and it satisfies the initial boundary condition at 0, t equal to 0, and U is also in H to K and satisfies the terminal conditions. This is the set of such functions. And so a weak solution is regular, so it satisfies these regularity assumptions, but the Hamilton-Jacobi equation is satisfied in this sense, a variational sense. I will give a little bit more intuition about this, and this is for the Fokker-Planck equation. So the terms that appear here, that are appearing here, are nothing but those that were appearing in the equation. I mean, after integration by parts. And these two identities have to be satisfied for all test functions W and V in the corresponding spaces. And what, I mean, one way to see these notions of weak solutions to the regularized problem is they are sub-solutions to the Hamilton-Jacobi equation in the distribution sense. In the sense of distributions, they are sub-solutions to the Hamilton-Jacobi equation. And there is a sigma that should not be here, sorry for this, and satisfy pointwise the Hamilton-Jacobi equation in the set where we know that M is strictly positive, okay? And regarding the Hamilton-Jacobi equation, it really satisfies pointwise, so the Fokker-Planck equation, okay? Okay, now, under the assumptions, exactly the same assumptions that I was stating before, so nothing hidden here, we can prove that there exists a weak solution to the regularized problem exactly in the sense of that I was defining before. And we have to establish a priori estimates. The way we go about it is establishing a priori estimates. Then we prove existence and uniqueness of weak solutions to a minimization problem associated with the Hamilton-Jacobi equation. Somehow that will give me M, the M epsilons. We prove existence of and uniqueness of solutions to a bilinear form problem associated with the Fokker-Planck equations. Those are going to give me the U epsilons. And then I really have my pair M epsilon, U epsilon that I'm looking for using a fixed point theorem. So this is the strategy. And once we have that pair, then using all the assumptions that I was mentioning before, and I was saying that many of them were for these a priori estimates and also for compactness, we can prove that this unique solution given by the fixed point theorem is bounded with respect to epsilon in the appropriate sense. So there is, you remember there was this MG, so we are going to have this bounded. And so this is how we get compactness for M epsilon, and for U epsilon, we have bounds in L1, W1, gamma, and so we have a candidate for weak solutions. So now how do we put everything together? So this is the first step. So remember that one thing that I said was very important was to establish that the regularized problem was monotone. It's monotone. So that's the way we constructed it. And then we can separate into two parts. So the one with the test functions in the domain of the operator, and the other one where it is written in terms of m epsilon. Okay, so we separate into two parts. Now, this part, so and actually we can okay, because I have a weak solution to my regularized problem, I have a sign for this term. Okay, so these were properties established for the strong solutions. It's not a strong solution, but it is a almost strong solution, and I have a sign. This is no negative. So with the greater or equal than 0. So with this is less or equal than 0. So this is less or I can write it. Then I look at this term. This I can discard. This one I can write into a term plus another one. I'm not showing you here what is C epsilon. I'm almost finishing. I'm not showing you what is C epsilon, but it's something that that it is, I can like it has this pointwise convergence that I was mentioning in the Mintis problem. It is terms that I can pass to the limit and prove that they go to 0. And here it is the strong weak property that I have to apply. This converges strongly. Obviously, there's no dependence on epsilon. This converges weakly. This has to do with the compactness property. We can pass to the limit, and that's how we get a weak solution for the original mean field gain problem. And just to conclude, just to say that we also, this is a completely different paper. It was using a completely, this is my last slide. This was a completely different paper, but just to say that, and it was to deal with planning mean field gain problems in which you are given not a terminal cost, but initial distribution and final distribution. We could use this approach to deal with some planning problems in the congestion case, which were new in the literature, and things that are ongoing. It is proving some kind of strong weak uniqueness for these solutions. And also we are looking at this application of these ideas to construct Asian-Riemannian gradient flows that we expect and hope to lead to efficient numerical approaches. I'm sorry, I took a bit more time than I wanted to, but with this, I thank you for your kind attention.